We are starting our unit on probability, which again is something you would have covered in 8th grade math class, but again, been a minute since we've been there, so let me give you some refreshers here. Grab a highlighter because there's some things I'm going to want you to highlight throughout the notes today and put little stars and circles and underlines around. The first one is the most basic word for us this unit, which is probability. You've probably used that word in common language a few times. You know, I will probably go, I've said the word a bunch of times, probably go here after school, there's a good chance it's going to rain. Those are all probability measures. Probability is measured from 0 to 100. 0 meaning it is completely impossible for that event to occur. So when you're like, it's a 0% chance of it raining, it means it's an impossibility for it to occur. Although we know with Texas weather, it's never an impossibility. If it's 100%, that means we're 100% certain that it's going to happen. So if you get a probability of 1, which is 100%, it is guaranteed to happen. If you look outside while it is actively raining, there is a 100% chance that it is raining, that sort of thing. Now, the different kind of outcomes we can have from a probability experiment, that is just called the outcome. So when I'm talking about results of an experiment, we're talking about the outcomes of that experiment, the possibilities for what could happen. If you're flipping a coin, your outcomes are heads and tails. Those are your possibilities. The sample space is the vocabulary word that stands for the set of all possible outcomes. So if we're saying we're flipping a coin twice, we could get tails, tails. We could get tails, heads. We could get heads, tails, or heads, heads, 2 in a row. That's my sample space because those are all of the possibilities of the outcomes I can get with all of the different things I'm measuring or experimenting with. But what we're really going to focus on today when we talk about probability is theoretical probabilities. Okay, so theoretical probabilities are not experimental. They're not done in real life. We're saying, okay, well, there's a 50-50 chance of getting heads and tails when you flip a coin because there's only 2 options. That's a theoretical probability. The way you calculate theoretical probability, I want you to put a cloud around this because we're going to use it all day, is theoretical probability is the number of favorable outcomes divided by the total number of outcomes. So, for instance, if you're flipping a coin twice and you really, really wanted it to land heads, heads, okay, there's one chance for you to flip a head and then flip another head, but there are 4 different combinations you can make. Tails, 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 heads, heads, tails, heads, heads. There's only 1 out of 4 chance of that happening. Now, if you actually were to flip a coin, that's called experimental probability, and that's not what we're talking about. We're talking about just in theory, in possibility, what could happen. The number of favorable outcomes divided by the total number of outcomes. I'm going to back up for a second because I missed highlighting this really important thing for you. You know how math makes up its own notation and language for a lot of things? When we're talking about probability, we write it as P with an A in the middle. It kind of looks like function notation where you would say f of x. But we don't say it like that. We say probability of A. So don't say P of A, it's probability of A. So probability of getting heads when you flip a coin, that sort of thing. Sorry, I forgot to talk about that. So let's practice. It says a student taking a quiz randomly guesses the answers to 4 true-false questions. So they just got the 4 blanks. They're like, well, the option's either true or false. I'm just going to take a wild guess and just guess all trues, all false, some combination of true and false. The table below shows the sample space, meaning every possible outcome for him doing this. Let C represent a correct answer and I represent an incorrect answer. The possible outcomes are, and then we look here. So just to make sure we understand what we're looking at. When it says I, what does that mean for this person taking this quiz? They randomly guessed, and what happened? They say what? Well, they guessed on 4 questions. What is it telling us in this question the I stands for? Read the little blurb. What does it say the I stands for? Incorrect answer. So if they got this, did they get any of them right? No. So they wildly guessed and they got all 4 wrong. Okay, what's happening on this row that says 1? How many C's do you see in these options? 1. So they guessed, they got 3 of them wrong and they got 1 of them right. What's happening on the row with the 2? Talk to me. What's happening on the row with the 2? How many C's do you see?
2.
So how many did they get right?
2.
Okay. On the third row, how many C's do you see? How many did they get right? Okay. On the last one, how many did they guess and get right? All 4. Okay. This is what happens when you randomly guess on a true-false test. You could have these options as what you get right or wrong. The question here says, what is the probability of the student guessing exactly 2 correct answers? So let's underline that. Exactly 2 correct answers. How many outcomes are there where they guess and get exactly 2 correct answers? I see that there are 1, 2, 3, 4, 5, 6 chances for them to guess exactly 2 correct. Do we agree? Okay, if we're doing that theoretical probability, we would say the probability that they get exactly 2 right would be the number of favorable outcomes, which we just counted to be how many? How many in the row with 2? 6, divided by the total number of outcomes. Okay, well, we have this entire table. How many total outcomes were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total outcomes. So now we just need to do a little bit of arithmetic. You probably want your calculator for this. What is 6 divided by 16? It's a decimal.
0.375.
Great, 0.375. Now we just did a whole gim kit on how to change decimals to percents. Because when we talk about probabilities, we want to say it in percentage. 0% chance of rain, 100% chance of rain. So if we were to change 0.375 to a percentage, what would that number be? 37 point, I think it would just stay as 5. Because there's no number behind it. 37.5% chance of wildly guessing and getting 2 correct. Maybe this is why we shouldn't wildly guess and we should study for our things. I don't know. Commentary. Part B says, what is the probability of the student guessing all of the correct answers? They only got 1 opportunity to guess all of them right. So if we do that probability, here's what I'm talking about, by the way. I'm talking about this one right here. There's only 1 outcome where they guess all 4 of them right. So the probability that they guess all correct would be 1 out of how many total options again? 16. My calculator friends, what is 1 divided by 16?
0.0625.
Great, and if we change that from a decimal to a percentage, what is that percent? 6.25% chance. If you wildly guess on a true-false test, you only get a 6.25% chance of getting them all correct. Again, maybe just a little commentary on why we should study for things and not just wildly guess. Okay, so again, this is a theoretical probability here. This is not what actually happened when a bunch of students actually did this and guessed randomly on a test. But just in general, these are the outcomes we can expect based on the numbers that we have. That there's only 1 way they can get all 4 correct answers out of the 16 other opportunities for combinations of answers. So 1 out of 16, the favorable outcome divided by the total. Are there any questions about that concept of theoretical probability? Okay. I'm going to introduce to you a new vocabulary word. It's called the complement of an event. The complement of an event, or you're going to see it shortened as A with a little floating C or A with a little floating like apostrophe. It means a complement. Consists of all of the outcomes in which the event A does not occur. Since the sum of the probability of event A and the probability of the complement of A is 1, we can use the following formula. Let's highlight. This one's going to be really important, or put the little bubbles. The probability of A complement is equal to 1 minus the probability of A. And the reason that this is, if you look at the image that we've given here for the sample space, if this rectangle represents the entire sample space that could occur, and right here is your event A. This is guessing all of the answers correctly. Then any other option, any other outcome that is not this is called a complement. If the whole universe right here, the universal set, adds up to 1 and you just don't want this part, you just take 1 minus the part that you don't want and you get the complement. That's where we're getting this formula from. Kind of like when you take area out of another area. It's exactly that. So let's see what happens if we do some complementary probability. Practice number 2 says you spin a spinner with the numbers 1 through 5 on it. I'm a visual learner, so let me draw myself a picture. Here's my spinner. I'm going to have 1, 2, 3, 4, 5 slices. I'll number them 1, 2, 3, 4, 5. There's my spinner. That way I can visualize what's happening. It's a pizza cut into 5 equal slices, a pie, whatever food item you want to cut into 5 equal pieces. They don't have to be perfectly drawn, so if you actually accidentally end up with 6, just erase one of the lines and make it a really wide one. It's fine. We're using our best drawing habits here. All right, it says find the probability of getting a 4. Okay, if I want to get a 4, how many opportunities do I have to spin the spinner and get a 4? Don't overthink it. 1 chance, yeah? There's only 1 spot with a 4 on it. So I would say that the probability of getting a 4 would be favorable 1 time out of how many options? 5. All right, calculator friends. 1 divided by 5, what is that as a decimal? And then we'll change it to a percent. 0.2, which is what percentage? 20%. All right, so we get a 20% chance of spinning the spinner and it randomly landing on a 4. Part B goes on to say, okay, yeah, cool, whatever. But what if you had the probability of not getting a 4? Like that's the whammy. That's the like you lose all your money thing in Wheel of Fortune, okay? What is the probability of not getting a 4? Well, since we know about complementary probabilities, we would say the probability of not getting a 4 would be equal to 1 minus the probability of getting a 4, which we just found out. We just learned that the probability of getting a 4 is 0.2, or 1/5. In fact, let's use the 1/5. I think that'll illuminate some things for us later. 1/5. Calculator people, 1 minus 1/5, I'll fast forward for us, is 0.8, which is what percentage? 80%. Awesome. Here's what I want to point out to you. If you look at my spinner that I drew, how many options do I have that are not 4? How many options do I have that are not 4? 4. Out of how many total? 5. In your calculator right now, do 4 divided by 5. 0.8. What is that as a percentage?
80.
Look at that. It's just what we got, right? So complementary probability is just the same as calculating the theoretical probability of the thing not happening. Occasionally, though, it is easier to use this complementary probability formula, 1 minus the probability, especially when we get into complicated things. But for right now, you could do it the old-fashioned way and just say, well, this is the same as 4 out of 5. That's 80%. I want you guys to work on B and C. They go together. I know there's 2 B's, but the second B. It says find the probability of getting a number that is less than 4. So if we want a number it's less than 4, what numbers are less than 4? Okay, I'm going to leave you with that. You're finding the probability of getting a number that is less than 4. I'm going to stop talking and let you think. I would like for you to do both B and C. Let me help, because at this point I think we either passed B or we're stuck on B. Remember, theoretical probability is the number of favorable outcomes divided by the total number of outcomes. First of all, our spinner has 5 numbers on it. So what's the total number of outcomes here? 5. The total number of outcomes, the most number of things we could spin and get is 5 different things because there are 5 numbers on my spinner. Okay, now how many numbers on this spinner are less than 4? 3. So we should be doing 3 divided by 5. When we do 3 divided by 5 in our calculator, we'd get 0.6, which is 60%. Awesome. Because again, these numbers, 3, 2, and 1 are the numbers that are less than 4. If we wanted to figure out the complement of that, find the probability of getting a number not less than 4. Again, complementary probability just uses that same probability. So the probability of not less than 4 would be 1 minus the probability that we get less than 4. But we just found that out. What was the fraction that we used for probability of less than 4? 3/5. What is 1 minus 3/5? 0.4 or 40%. And again, this makes sense because this number here and this number here add up to how much? 100%. That's what we need. It has to equal to 1 or 100%. Those weatherman probabilities, when we actually run these experiments and see what actually happens, are called, on the back, experimental probabilities. So the first one is called theoretical because it's all, I don't want to say fake because that seems weird, but it's all brain thinking, counting the numbers as it should be. Experimental probabilities are probabilities based on repeated trials. We have to have evidence of this. We have to run some experiments and actually take down numbers to see our experimental probabilities. But experimental probability works almost exactly like theoretical probability in the fact that the formula for experimental probability is still the number of successes or favorable outcomes divided by the number of trials or number of times you tried the experiment. So favorable over total, same idea. You're just actually running the experiments this time. Not necessarily saying there's 5 things on a spinner. I'm actually going to spin the spinner a certain number of times. So problem number 3 says, at a school dance, the parents sell pizza slices. The table shows the number of pizza slices that are available that a student can choose from. They can choose a slice at random. That's important for us that they choose it at random. Let's look at our given information for a second. What are the 2 kinds of pizzas they can choose from? Pepperoni and cheese with what kind of crusts? Thin and thick crust. So really we have 4 options here. They can get a thin crust pepperoni pizza, a thin crust cheese pizza, a thick crust pepperoni pizza, or a thin crust cheese pizza. So this is kind of like a Punnett square where it's telling us how many of each we have, yes? Just as, because I know we need this information, and these are called two-way tables, let's find the total number of pepperoni pizzas, okay? If we just wanted the total number of pepperoni pizzas, we'd add up the thick and the thin crusts for how many total pepperoni pizzas? I need your brains to turn on. What is 34 plus 8? 42. So 42 total pepperoni slices are available. How many cheese slices are available? 48. So that's how many cheese slices are totally available. What if I changed my mind though and I'm like, well, I really want a thin crust pizza. How many total thin crust pizzas are there available? I don't care about the topping. So if we add this direction sideways, there are 70 thin crust slices available. How many thick crust slices available? 20. What's 20 plus 70? 90, guys, 90? Yeah, 90. Okay, well, what's 42 plus 48? Also 90. Okay, so here's what we noticed about two-way tables. We're going to see these a lot. They all have to add up to the same number in this bottom corner. The total number of thin crusts plus the total number of thick crusts have to add up to the total number of pepperoni and total number of plain cheese. That's just something to check for yourself to make sure you're adding numbers correctly. They need to all add up to end up being the same thing. Okay, let's actually read the question here. Now that we've digested what two-way table they gave us. It says, what is the probability that the student chooses a thin crust slice with pepperoni? Okay, let's find that in the table. So thin crust pepperoni. How many students picked thin crust pepperoni pizzas? 34. Out of how many students that picked any sort of pizza at all? 90. Okay, so now we know our experimental probability here was the probability that they got thin pepperoni was exactly 34 out of the total number of trials or total number of slices, which is 90. So that was the total number of thin pepperonis over the total number of slices. Calculator friends, what is 34 divided by 90? Mm-hmm.
0.37. I mean, there's a lot of sevens.
Yeah, and we'll round it up to 0.378 because it's like 3.77777. We'll round that up to 3.78, which is what percent?
37.8.
Fabulous, 37.8%. So again, it feels like we just did theoretical probability, but theoretical probability would be 1 out of 4 chance because there's 4 options and they got one of the 4 options when in fact we didn't get 1 out of 4%. We got 37.8%. So your experimental probability and your theoretical probability may not match, which is interesting. Part B, what is the probability that the student does not, let's make sure we circle, highlight, star, underline that word, not choose a thick crust, plain cheese pizza. To figure out a not probability, we need to use complementary probability. So first thing we need to do is actually figure out the probability that they chose a thick, plain cheese. Okay. Looking at your table, how many students chose a thick cheese pizza? 12. Out of how many total slices again? 90. Calculator friends, 12 divided by 90. 0.13 and then a whole bunch of 3s, yeah? Okay, we'll leave that as 0.33, which is 13.3%. Okay, cool. That's not actually answering my question, though, right? Because we didn't ask how many students did choose a thick crust plain cheese pizza. We wanted the opposite of that. So we go back to that complementary probability, the probability that we do not have thick cheese. That formula was 1 minus the probability that we do have thick cheese. Well, we just got the numbers for thick cheese. So when I do not thick cheese, all I have to do is 1 minus that 12 divided by 90. Now, I'm actually going to show you my calculator for this step because these are the decimals we've been using before were really easy to figure out. This one's less so. If you did not get your calculator yet, go grab it because I need you to follow along with me. Okay, so one thing I've noticed so far, just in this math that we're doing, we don't really want fraction answers here. This is like the one unit where I'm not going to prefer fractions over decimals because, again, we want to answer in percentages. It's easier to get to a percent from a decimal. So I have you well trained to always use the fancy fraction in this calculator. And I'm going to tell you to forget that for a second. Here's how I want you to type it in. So now that we've typed it in the way we need to for this, to keep it as a decimal, we'd get 0.867 which if we round that, or sorry, not round it, but change that to a percentage, it's 86.7%. Questions, comments, concerns? Do we see how to set up these formulas? The number of successes divided by the total number, which means anytime we're doing an experimental probability, we have to know the number of trials or the total number of pizza slices that we've done. You'll notice on the paper it says, in a geometry class, oh, look where we are. Students took turns throwing crumpled paper into the trash can. We're going to use the results to run some experiments and find some experimental probabilities. So what I need for us to do, okay, honestly, before we get started, we're going to make this simple for ourselves. I know that because of our talents and our abilities, it is not a 50-50 chance of you shooting the paper into the basket and making it. Because mine for sure would not be, because I cannot play basketball to save my life. But we're going to assume that everybody has a 50-50 chance of taking their wadded up piece of paper, throwing it into the trash can the same. So everybody right now who got their piece of paper back from me, go ahead and wad it up. We're going to take turns coming to stand, I guess maybe here, behind this chair and shooting your paper into the basket. Now, as a class, we need to tally up the number of people who make it and who don't make it. Okay? No judgment on not making it. I would not make it. Who would like to go first? If Angelina makes it into it, we're going to put a tally mark on the made it into the trash can. And if she did not make it, we're going to put a tally mark on the did not make it into the trash can. Are you ready? Go ahead. Good luck. 50-50 shot. We're pretending we're good. All right. Where do we put the tally mark? Yes, please. It did not make it in the trash can. Put a tally mark right there. All right. We need everybody to come up here. So if you have a piece of paper to wad up, come up here. You can write down the tallies whenever we're done because I'll have them up on my board. Yeah, come on up. Thank you for being first. I appreciate you. All right, we've got our experiment here. How many of us made it into the trash can? 2. How many of us did not make it into the trash can? 12. Okay. Now remember, we're pretending that we all have the same skill set and ability, and there's a 50-50 chance of making it into the trash can. I know legitimately that it is not, that we all have different abilities, and it is not a perfect experiment, but bear with me on this. Okay. It says, what is the experimental probability of the crumpled paper making it into the trash can? Okay, experimental means we're using our data. If we want the probability of making it, we want the number of successes. How many people made it into the trash can again? 2. Out of how many people who shot their ball into the trash can? 14. What is 2 divided by 14? Calculator friends. Oh, that's 14 divided by 2. Yeah. This is definitely a calculator heavy unit because it's going to be a bunch of decimals. What you got? Okay, we'll use the first 3. So he's saying 1.14, and then we'd have to round that to a 3, which is what percentage? 14.3%. Okay, so we got 14.3% of people made it into the basket. Part B says, wait, but what was the theoretical probability of making it into the trash can? So this time we're not using the data. We're going to go back to the theoretical probability formula, which was the probability of making it being the outcomes. The outcomes in this experiment were either you made it or you didn't. How many outcomes is that? You made it or you didn't. How many outcomes? 2. How many of them were favorable? We wanted them to make it, yeah? That's one of those 2 outcomes. What is 1/2? We should not need a calculator for this one. What is 1 divided by 2? 0.5, which is what percentage? 50%. So look at the difference. Our theoretical probability said that we had a 50-50 shot of making it. But when we actually went in and did the experiment, did that match up with the theoretical probability? No, this is why the weatherman's wrong. He looks at all the numbers. He says there's a 50% chance of rain or a 60% chance of rain. Then you walk outside, you're like, bro, it ain't raining. That's because that's the experimental probability of it actually occurring versus the theoretical probability based on numbers and theory. Do we see the difference?
Yep.
Let's do it again then. So part C says, what is the experimental probability? Experimental means we're using the data in the table. Experimental probability of the crumpled paper not making it into the trash can. Okay, we can do this. So not making it. How many people did not make it? Out of how many total who took the shot? Ooh, 14. Yeah, total. All right, calculator friends. 12 divided by 14. Give me the first 3 decimals, please. 0.857, which is 85.7%. Okay, that was what actually happened when we ran our experiment. But let's think theoretically here. Again, the probability of not making it. We only had 2 options. You either made it or you didn't. Which one was favorable if we want the probability of not making it? That's 1 out of 2 of them. Again, what is 1/2 as a decimal? 0.5, which is what percent? 50%. Again, our experimental probability and our theoretical probability were not the same. That's going to happen because theoretical and real life are usually kind of different. However, in a well-done experiment, which this was not, because again, we all have different ability levels and we all stood at different points in the room, blah, blah, blah. I get it. It wasn't actually a 50-50 shot of making it. But in a well-done experiment, if you do enough experimental trials, then your experimental and your theoretical should converge to the same number. Again, this was just like a cute example we could do in class, not the perfect example that we could always go with. The main idea of this lesson is understanding the difference between theoretical and experimental and when to use the different kinds of formulas. So that's really easy to see here. When it asks for experimental, we use the data in the table. Oh, I missed part of the table when I did that. Okay, when it says experimental, we use the experiment. When it says theoretical, we think about the total possible outcomes and the favorable outcomes, like true or false, or in or out, not necessarily what actually happened. Okay? Sorry, to help establish the fact that these two are different, you're going to run an experiment for your classwork. Now, this is homework if we don't finish it, but like most likely you'll finish it because it's not going to take you that long. What we're going to do, it says on Google Classroom, select either the online dice roller or the dice spinner. I did not actually post this for you, so go to Google right now, and in the Google bar, just Google the words like spinner, and it will give you a spinner, or if you'd rather roll dice, Google the word dice. I need you to have a 6-sided spinner or a 6-sided dice. So a typical dice or a 6-sided spinner. You should be able to figure that out on there because either there's websites for it or the actual Google spinner will pop up, kind of depending. Make sure it has 6 options, whatever you pick. And if you're like, the spinner thing's looking weird, again, just look up an online dice. I need a 6-sided dice. What you are going to do is you are going to run an experiment for yourself to see the difference between theoretical and experimental probability. You're going to do your event 25 times. So spin the spinner 25 times or roll the dice 25 times and mark down, kind of like we did with the trash can, the frequency of each of your results. Your results are as follows. You're either going to spin or roll a 1, spin or roll a 2, spin or roll a 3, spin or roll a 4, spin or roll a 5, spin or roll a 6. Those are your only options as a result. You're going to tally up your results like we did with the trash can thing, count up your frequency, and then find your experimental and your theoretical probabilities for both. I put both of the formulas down there at the bottom for you to be able to do this. You have the rest of class to work on this experiment and be done. So work at your own pace, but you're working individually. Everybody should have different data because you're running different experiments. Are there any questions? I know there will be, but are there any big questions, I guess I should say. Okay, so first things first. Find a dice or a spinner and do the spinner or dice 25 times and log your results.